Hello and welcome to Refactoring Bitcoin. On the screen here, you can see the current state of my outputs function. And in the error message, you can see what the expression here actually produces. You see above I have this convert function, which I pass to transform, which is then used with this pipe expression here. And if we look in the error message, we see that here, this is our function signature, and the function is passed by pointer. But why is that the case? I don't use an address operator here, so why is it passed by a pointer? And if I add an address operator and then look at the function return type, I see it's actually exactly the same thing. So whether I use the address operator here or not, it seems to work identical in both cases. But why is that the case? Is there some template magic happening inside transform? No, the actual thing is that this behavior is inherited by the C++ programming language from the C programming language. So how that exactly works, I want to show a few examples. So let me switch to Compiler Explorer. So this is Compiler Explorer with the default example. It always this square function here. So let me switch to C. We have the same example here. So in this example, I will create a main function. And in the function, I want to store a pointer to that function square. So the function square, I say it's a FP, it's a pointer. It returns int and it takes int. But the compiler will interpret this as a function that returns a pointer to int. So I have to wrap the star and the FP in parentheses to actually tell it that I want to have a function pointer. And now I can initialize that with the address of square. Now it compiles, right? It compiles. If I want to call the function, I dereference FP and I pass the value 2. And the compiler also doesn't know what to dereference here. I also need to wrap this in parentheses, and then I can simply return it. That compiles, and it's working. But it looks quite ugly, right? So the designers of the C programming language thought it would be much nicer if the syntax for calling a function through a function pointer and calling it directly would be identical. So this dereferencing here is actually not needed. I can remove the parentheses and the dereferencing, and this will also work. And the same is true for this address operator here. It can also be removed. So that looks much, much nicer, right? So, but why does that work? Why can I use the function here directly? The correct name for that is a function designator in C terminology. And the rule is that function designators decay to function pointers in most cases. Only in most cases, right, there is one exception where it does not decay, or there may be more exceptions, but the thing that I want to point out here is that when I use the address operator, then the function designator does not decay into a function pointer, because otherwise I would take the address of the function pointer rather than the address of the function. So if I use an address operator, the function designator does not decay, and I can take the address of the function. If I do not use the address operator, then it will decay, which will also result in the address of the function. And therefore, if I use an if condition, and I want to check whether square is identical to the address of square, that condition will always be true, because in this case here, the function designator decays into a function pointer. In this case here, the function designator, it does not decay, but I take the address of it, which will result in the same address of the function. So therefore, the condition is always true. But that also means if square decays into a function pointer, then of course I can dereference that pointer, which will result in a function designator, which will then decay into a function pointer, which will, I can then dereference, of course, into a function designator, and then it will decay into a function pointer unless I add a address operator. So it will not decay, but it will be passed to the address operator, which will give me the address of the function, which of course is a function pointer, which I can dereference, and so on and so on. I can sprinkle dereference, I can sprinkle address operators here as well. This will not change anything. What I cannot do is add two address operators directly next to each other. That will just be invalid syntax unless I add some, for example, unless I add this. The important thing, it's only important that it needs to be an even number. So this will just be interpreted as a C-style comment, right? You can write some arbitrary text in here like this. Okay, so this will just resolve in a function pointer. And we can see if we copy the code and if we switch to C++ and we paste it, it will also compile to just the right thing, to the same thing. We see that the rules for function pointers, that the functions decay into function pointers is the same in C++ as in C. But why am I telling this, right? Why is it? Is this something that you have to know? So I want to show you something else. Let me add a few includes. I want to include algorithm, and I also want to include array. And let me add using namespace. In production, I hate to see using namespace std. Never use that, never do that. But in this example code here, it's quite convenient to make the code fit on the slide. So inside the main function, I want to define an array. Just call it A. It will be just a simple array with just two elements. And I will initialize it with just some random numbers. And I will define a second array, int b, which is not initialized with numbers. And then I want to transform the first one into the second. I use the transform algorithm. And I will transform from the input array, which is A. So I say begin A to end of A. And the output will be the begin of B. And the transformation function will be just this square function. Okay. And then in the end, okay, this needs to be an array, of course. And then in the end, I just want to return, let's say, the element at index 1 in array B. Oh, sorry, B. And that will compile. And I can see in the output here, we have a function call to std transform. But if I enable compiler optimizations, then it will compile to just the function call of square, right? So it will inline away, it will optimize away the array, the transform calls, everything. The only thing that remains is this value 7, which will be passed to square, and then the result will be returned directly. So why is this function not inlined? If I add the inline keywords, let me compile and I see it actually generates more code than without the inline keyword. So that's not a good idea. Let's remove that again. Okay. Why is the square function not inlined? The reason is that the function used as the argument in transform decays into a function pointer, which cannot be, if I pass just the address of the function, the compiler does not know what's behind this address. Okay, so if I use the address operator here, you see the compiler produces the same code. And if I use the dereference operator, of course, the function decays into a pointer. I can dereference it, it decays to a pointer again. So it will be a function pointer and therefore cannot be inlined. But I want to show you a trick. I will wrap this function here into a struct. Say a struct, and I don't give it a name. I just close the struct here, but I will create an instance of that struct, and I will call that instance square, like this. And now I get a compiler error in this place here, because it says that this square here does not have this dereferencing operator, of course. And if I remove that or turn it into the address operator, I will get a compiler error that a pointer to this square cannot be called, or that square cannot be called, because all that square has is this member function called square. But I can replace that member function with a function call operator. And now I see that the whole program is optimized to just this constant, which is the square of the value 7. Okay, so with this struct here, I now have completely different behavior, right? So this struct is passed by copy, and the compiler, when it uses it in a call expression, it invokes the function call operator, which is defined inline here, and nothing is turned into a function pointer automatically. Therefore, the compiler knows how to inline it and can optimize the complete program to just a constant. So therefore, you have to keep in mind that if you want to help the compiler, then using functions can be dangerous in some contexts, because it will just create unnecessary hurdles for the compiler to optimize. But who writes all their functions in this syntax, right? I don't. But there's a different way in C++ to create unnamed objects with a function call operator. What I'm talking about is lambda expressions. So I can define the whole thing here as a lambda expression. So take this away and just add those brackets. And then I assign the whole thing in a constant expression to a value, say const expr auto square, and it will assign to the lambda, and I have to end it with a semicolon. And this now nearly looks like a function call, like a function definition. Very similar syntax, but now this helps the compiler optimize it and inline the function even when it's used in higher order functions, if I pass it to transform, like in this case. So if I switch back to my source code, then I see that this convert function is definitely something I do not want to implement as a function. I want to turn that into a lambda expression. So I add const expr convert, and I sign it with a lambda expression, and I have to add a semicolon in the end. And what I can also do is take the whole convert function and move it to the place where it's actually used. And if I format, much better. And now the compiler will be able to inline that, but I still haven't fixed the actual return message and return compiler error. If you want to follow me if you want to learn for other C++ tricks, make sure to follow me, subscribe to the channel. Thanks for watching. Goodbye.